All right, so thank you for still coming after lunch. I know it's harder. I want to continue in that theme of looking at the data, looking at the neural tangent kernel, trying to understand the interplay and what deep learning does somewhat in practice. I owe you a slight correction and maybe a recap from the last lecture. Let's see how I work it out with my glasses. So last lecture I presented two separations, you might recall. One I actually tried to hand-wavily prove, but at least prove a little bit. The other I didn't, and I actually didn't give it right. So I want to correct that. And Lenka asked me also what's the intuition for the separation. So let me just write a little more and wave my hands a tiny bit more so that maybe the intuition will become a little more clear. So remember, there was the separation that we did by Malach and Shalev-Schwartz last year, right? And remember, our function was simply, let me write this, a hidden consecutive pattern, right? Consecutive K pattern. G. Right, which was hidden in a large dimensional space. Oops, sorry, but it was actually just mapping K consecutive bits to some outcome. It was some Boolean function. We didn't really care which one, right? And it was embedded in a function f in a much bigger space, which we keep calling D, such that there was the secret index J, right? Such that basically f of x was equal to G of x of these xj and xj star 1 plus 1 and so on up to xj star plus k minus 1, okay? Remember this? And then I waved my hands for a long time to show you, I think you all for some reason bought that there is a lower bound with gradient descent, as long as there's full symmetry. And I justified it by saying that the moment you have full symmetry, especially in particular if you have permutation symmetry, you will not know anymore that these are consecutive bits. You're reduced to 20 years of hard work in theoretical computer science that has shown that the problem is hard. But also we see that when there's something symmetric, it's difficult to solve because gradient descent also does something kind of symmetric and something with an ensemble. Okay, so far so good. And then I gave you, if you remember, I gave you a construction. I constructed a convnet, right? And the trick, and maybe I didn't write this down, but I want to write this down one more time. The trick is that we basically say any function, and this is very stupid, can be written on k bits, can be written in this form, a sum over all bit string z, an indicator function z x. So this function is one if and only if the bit string z matches the bit string f, g of z. So this is obviously true, right? I mean, obviously, I can write this in this cumbersome way, right? And then I convinced you, hopefully, that each of these indicator functions, right, could be achieved by one filter. Here's our k bits, by a filter of weights of size k. So this weight vector w would achieve an indicator function. So let's give it a label z, right, in Rk. And in fact, what they did, they put it into plus minus 1 over k, right, to the k. Okay, same k, remember? And then I showed you basically that if you throw these weights at random with plus minus signs, then the way these pluses and minuses land will define this z, basically, right? So we can say that z, if you wish, is the sign of this weight vector here, w, here, this particular one, okay, for this one filter here, right? So you just take the signs. This gives you the indicator function if you have a nonlinearity that moves the zero back and forth and then you use a max, right? And then we argued that, okay, this is how you construct such a thing, but we're not allowed to construct anything. This is supposed to be learning. So instead of constructing, we just throw these weights at random. And we know that there are 2 to the k such combinations, right? Combinations. So such z's. So we need to throw 2 to the k times k, coupon collector, many such weights, such filters, such channels into the space. And then we'll get at least every indicator function 1. And in fact, we expect to get log many of each, roughly, right? And there is a bit of a variance here, okay? So we throw enough of those, and then we use the next layer to basically just learn this function here. But because k is log d, everything here in that space is size n, and so that becomes, it has become a linear problem, and we know gradient descent can solve it efficiently, right? Remember this? Now, some people came to me afterwards and said, okay, but what about these weights w? If you do true, first of all, remark number 1, you can kind of do this in the random feature model if you wish, right? You freeze these, you throw the w's and then you freeze them. Remark number 1. Remark number 2, we don't actually, I mean, I, as a computer scientist, I like this, but you physicists don't like this. You like Gaussians. But what do? Instead of throwing plus minus 1 over k, we simply throw a Gaussian. So instead of this, it's enough to throw a normal with sigma squared 1 over k squared. If you throw that normal instead of plus minus 1 over k, on average, you'll get values in that Gaussian here that are of order 1 over k. And that's enough. Proof still works. Just throw a few more. Remember when I showed you that theorem? It wasn't a 2 to the k. It was a 2 to the k plus 3 there. So, add a bit more. Make sure the Gaussians basically mostly have either plus 1 over k or minus 1 over k. A bit of deviation doesn't matter. Just throw enough at this. Clear? Okay, so that's number 1. And then you can freeze these Gaussians. You can freeze these weights, and you can just learn the top layer. Right, so that's remark number 1. This is actually a kernel kind of method, if you think about it. I don't know what to make of it, but just want to point this out. But remark number 2, what if we actually want to use true gradient descent also on the W's? I mean, if we're not allowing to freeze weights, then they show, because there's so many of these W's, they actually show that gradient descent doesn't move them very much. Gradient descent mostly moves the stuff in the next layer, of which there are much fewer, much sparser, so to speak. Okay, so the proof is actually really, it is a real proof. It's not just, let's not cheat here and let's cheat there. It's a real proof where they first show the W's don't move so much. Gradient descent on the second layer is enough. And you can do Gaussians as long as you throw enough of these into the thing, okay? So that was just to finish that proof. And then I said there is the second separation. So this gives, just to summarize, right, this gives a separation between, how can I put this? So here, a fully connected net needs either super polynomial size or super polynomial time. Needs super polynomial resources, basically. That is what they show with the statistical query model, right? So in this case, think of it as at least n to the log n, which is too big. Or d to the log d, I should say, sorry. D to the log d, right? Whereas a convnet can do it in poly d, time and resources and everything. So there's a polynomial versus exponential separation, which computer scientists like, but which hopefully you like as well. So that's that one. Any more questions to this? I think hopefully it's clear now. And the other one, this was the one by Malach, then there was the one by Lee. I think Zhang and Aurora, but let's just say Lee et al. 21, where I told you there is a problem where you get a sample complexity separation between a convolutional and a fully connected one. Okay, so that was where a convolutional net basically can do it in order 1, so constant time and samples, doesn't matter, right? And a fully connected net, I wrote it down like this, but I didn't justify it, at least d squared. Time and also samples. Okay, and here I was not the problem. I got it wrong, but let me give you the real problem that they solve. So their input x is in 2D dimensional space, and it's simply actually it's a normal 0, 1 in 2D space. Okay, so I said it was a Boolean cube, but it was it's a Gaussian. And the reason it's a Gaussian is because they want to use the property that I mentioned, which I proved in the beginning, the equivariance. Okay, so note that these inputs, because they're Gaussians in 2D dimensions, they're invariant under rotations of the space. Any rotation, right? Because it's Gaussians. Gaussians have this nice property of being invariant under rotations. Okay? And y, the label, or f of x, actually, I had it written correctly, and then I got confused. So it's let me write it really correctly. It's the sine of the sum of the first squares to the first d minus the sum of the second squares, d plus 1 to 2d xi squared. So this is the function we want to learn. Okay? So let's think of this function for a second. It splits the inputs into two parts, the first half and the second half, and then it looks at the length of the first half. You know, it's a Gaussian normal, so the length squared is roughly d, right? It looks at the length of the second half, and it needs to decide, is this one longer or is that one longer? That's the problem we want to solve, right? And so you can convince yourself, I don't want to do it again because I make mistake. A very simple convolutional net with a squared nonlinearity can do this. You square it, you pool it. It's like with a pooling layer, you can do it, right? If you have the stride correctly, everything. Tailored to the problem, but you can do it. Very simple, right? So the question Lenka asked me is, why does a fully connected net need d squared samples? And not just d, because Lenka said to me, any separation I know of this type, there's always a d, and never a d squared. Can I cite you like this in this brutal way? So why is there a d squared? I'm just going to wave my hands, but think of this problem here. Once you give it rotational invariance, so now you are allowed to take this vector and rotate it whichever way you want, right? And then you have half the subspace in one half, so it points into two subspaces, right? You can split the whole space of dimension 2d into two halves of dimension d each. And the vector points in both of these directions. And you're asking, is it longer here or longer here? Right? Now, if you're allowed to rotate, so this is quantum. This actually relates to stuff I did before. So if you're only allowed to permute, okay, then how many permutations are there? About 2 to the d. So when you take a log, you get a d separation. I mean, I'm being very vague here, but permutations scale as 2 to the d, 2 to the 2d, whatever. But now we have rotations in big space, and choosing a subspace requires matrices. So think of choosing a subspace as a dumb process where you just randomly pick a matrix that rotates into that space. That means you need to pick d squared or 2d squared entries, roughly. So you need to distinguish 2 to the d squared subspaces, because you're in space. You're not just permuting. This is where the 2D is coming from. Does that help in terms of intuition? I'm not going to say, this is a complicated proof. It's not easy. Sorry? Question?
No, it does, because it boils down to the mistake that you wrote.
Yes, exactly. So, right.
It's just the sum of x.
If it was a sum of x, only permutations would have worked. Right.
It's just on
Fair enough. No, you were absolutely right. You were right. But here we're putting ourselves in space and we're allowing the whole space. So this is actually, when I did quantum computing, we always got d squared speedups as opposed to d, because we allowed ourselves to go into the whole space and not just the stupid bits, right? I'm just being now very vague, but this type of proof actually is known from quantum computing. People have done these type of, so you put epsilon nets on all the spaces and you count, and then you get 2 to the 2d as opposed, 2 to the d squared as opposed to 2 to the d, okay? So that's all I wanted to say about these separations. And now I want to pass on but before I do, I want to show a pretty picture. So in that paper here, the Lee one, this one, okay, they did an experiment. They wanted to be cool and do experiments. So here's what they did. they took images, I think 32, maybe that's CFAR, I don't know. Is CFAR 3 times 32 times 30? I think so. So they took CFAR images that have this dimension, and there are 3 channels, as you know, right? RGB. And they, what they did is they ignored one channel, and the other 2 channels, they just checked the sum of squares. So this basically embedded this problem here by asking, is it more blue or more green? Is it RGB, blue, red or green, whatever, right? That's what they asked. Is it more red in an Euclidean distance or more green? They really did this, and this is this one here. And here they have a bunch of these convolutional architectures, and that's all the good stuff up there. And then they have a bunch of fully connected architectures, and that's this. And here is a logarithmic scale of training data. And it shows, okay, CFAR is not exactly Gaussian, right? But even there, you see that separation in practice. And then instead of CFAR, they just used Gaussians, right? They initialized each channel as a Gaussian. So it's literally this problem here, right? And they again showed that these these convolutional architectures are much more sample efficient than these fully connected ones. That's cute, right? I mean, you have to say it's cute. I found it cute. I mean, it's a bit, it doesn't fully relate because the convolutions, of course, weren't these ones that they used. They used more normal ones, but still you could see the separation. Okay? All right, so I was very quick on this one yesterday. I just want to write some, Yasaman basically prepared the territory for me, so I don't have to do much, but I do want to write down a few things about the NTK again, which I will use. And then I want to come back to this picture. But for now, I need maybe a little more board. Okay, so basically everything, I'm going to quickly repeat what Yasaman told us earlier this morning, but I will make it consumable for somebody who doesn't want to think so much or understand the whole theory or whatever. Anyway, so remember, there's a so-called Ntk parameterization, which is not exactly the one that we've seen first, which basically says that our network is, these are the parameters, this is the input, is given by weights in layer L+1. And then we have, so this is how computer scientists like to parameterize it, but I think that's also what, here's a nonlinearity and another weight in the layer L, right? And then this again, so we take these, we're normalizing outside with these are the width of each layer, right? And then we have another nonlinearity, and so we go until we get to square root of C over D1, right? And the last nonlinearity, and square root of C over D0. D0 is the input layer, and then we have the weights, and we get our input. Okay, and then we close a lot of brackets. Okay, so this is the so-called Ntk parameterization of the neural nets that we write. Okay, and what is the C? Actually, C is simply a bound on the nonlinearity. C, usually people think of it as, I just don't want to make a mistake, is the inverse of the expectation under Gaussian 0, 1 of sigma squared of Z inverse. Okay? So we're looking at our nonlinearity and we're thinking and hoping it's bounded, and then we can write a C. Okay? So that's just for these type of nonlinearities, right? And then we initialize, and the beauty is now we initialize with normal Gaussians, 0, 1 actually. So we put all these variance normalizations outside, and then our weights are normal Gaussians. And then we usually, we let all these D1 dl, kind of we set them to m and let them go to infinity. This is the not the Jacob way of letting it go to infinity, but kind of the Aurora and other people way of letting it go to infinity. Doesn't matter. And then when we do gradient descent with some learning rate, right? Then we do gradient descent with some learning rate, and we get that the weights evolve in time with some loss function, usually quadratic loss. Okay. And then we get this with some learning rate, and we take a gradient, right, of some loss function, which is usually square loss, and x. Doesn't matter. Forget the x. I mean, let's just think of it as a function of the parameters. And then we can think of, we do a Taylor expansion, just to get the way I think of Ntk. I do a Taylor expansion, right, around the initial, in parameter space, okay? Around the initial parameters, x, plus in a product of the gradient with respect to the parameters, f of the initial parameters, right? You've seen this more from Michael Jordan. That's Michael Jordan notation, more than maybe the others. And then there are these higher order terms, which we will argue don't exist anyway in the large limit. And then what we have definitely learned today from this morning's lecture, at least I have learned, if you don't want to have a headache, you set this thing to 0. Okay? And how do you set it to 0? I mean, you can say you set it to 0. What people usually do is they construct 2 neural nets. Have you seen this before? It's probably known, right? Use a simple trick. You construct 2 neural nets, g theta 1 of x, right? And g theta 2 of x. So you just build 2 of x, right? And you consider f to be the difference, and you initialize them similarly. I mean, with the same initialization. Same initialization, so to speak. And then magic. You don't need to deal with this terrible term where we really suffered today to understand better whether there's a k or an eta or whatever, right? So let's just avoid this if we actually want to do something that you know. So anyway, and then of course for very wide networks, right? So when they are wide, then folklore tells us that this is roughly this, although we'll need to bound it. And the neural net becomes linear in the feature map, which means that we get this kernel, which I like to write as a k. But if you want, I can write it as a theta, just to not, which is, right, just given by these features. F init, and x, and this gradient. X prime. And for all practical purposes, this is what we'll care about going forward in time. And the theorems, there are lots of theorems proved, but the flavor of the theorems that are proved that I like is that if m is bigger than epsilon to the -4, okay, polynomial in L is the depth, remember, and some logarithmic 1 over delta, okay, then with probability 1 over delta, then with probability 1 minus delta over the initializations. So you can make this as small as you wish. So with very high probability, you get that the kernel at initialization pointwise, okay, this is pointwise actually, xx prime, minus the actual kernel if you don't do it initialization, but at any point. So let me just write this as k. I should have. Okay, can you? Let's write the big kernel, since you like the big kernel. Like this. So pointwise, if you didn't do it initialization, but throughout the evolution, right, Point-wise, this will be smaller than epsilon. Okay, so this is the type of results that you can show as a trade-off of width and how much the kernel becomes a constant. Okay, and then we pick our widths large enough that this happens. But there's other results, and Yasaman mentioned them also, by Lee et al. That she mentioned today, which also involve the smallest eigenvalue of this matrix. So I'll write them in a second. And I mumbled something last time, but I want to have it written exactly. So if all this holds and we're in these good conditions, then we can say that everything is linear, right? And that means f evolves as simply, and remember we have set the first term to 0, something like this. And then here, the term we get here, I think I wrote this just for this reason, something that scales as 1 over square root of the width. So the error we make scales with the width, but not so terribly. I mean, 1 over square root, right? And then we get gradient descent is doing kernel regression, right? And we can write the solution. So the kernel solution of this thing, once you remove the parameters, is basically, so Yasaman wrote this as theta x, and x is the training data, okay? Train, right? Theta train. It's train, x train, I should say, sorry, twice. So this is just the kernel on the training data, okay, -1. And then here is the labels of the training data. Right? So this is when we do kernel regression, I should say, with the neural tangent kernel. Then we can actually write down the solution. And that's what we do. And that's what people then just take this expression and use it. And we'll do this in a second and get some beautiful results. But there's one more thing I wanted to mention, is when we look at the flow, at the gradient flow, whatever you want, we can look at basically what happens in time to our train data, right? And we can basically look at the loss. Or maybe we can just first look at the flow. So the flow is basically something like 1 minus, so the minus some learning rate, that nice kernel, t, okay, times y, train. And when I write this kernel without anything, just like Yasaman, it means on the training data, train, okay? So this basically shows how quickly we converge with our kernel, right? And in particular, why do I care about this expression? Because that allows me to write the loss function during training, x train, right? Minus y train, so the loss function, an L2 loss. And this can be written, basically, you just open these brackets here and rewrite it. And what you get is basically, you get the norm of e to the, what do we have, minus eta, this thing, remember, t, y, train. And why is this nice, squared? Because now we can do an eigenvalue decomposition of that kernel. Okay, so now we write that kernel here basically as some lambda I. There are as many eigenvalues usually. Let's hope. I mean, everything is non-degenerate in my world and whatever. So up to the number of data points, n. These are the eigenvalues, and let's say these are the eigenvectors vi transpose or tilde, whatever. I mean, this is the Eigen Decomposition, and if you insert this and write this here, then what you get is basically that this becomes the sum of the inner products of the eigenvector with the data, with the labels, y train squared. And here you get the e to the minus, what do you get? Lambda I, learning rate, perhaps, lambda IT. Okay, so that's the beautiful thing. With lots of approximation and back and forth and waving, the beautiful thing is that you can basically think of the shrinking here of the training, the speed of training, you can decompose it in the eigen basis of the kernel. And one of the things here is, remember Yasaman told you that the learning rate, people say it can't be bigger, so we better choose it large, but not too large, because otherwise it doesn't work. And remember, it was 2 over lambda, so she wrote lambda max, so for me that's lambda 1, okay, the largest eigenvalue. And when we plug this in here, what we get is lambda I, here's an I, divided by the largest one, lambda 1, okay? So the convergence during training is basically governed by what people call the condition number. So what is the condition number? Kappa is, I keep mixing it up which way it is, one way or the other. Let me write it down. It's lambda, the minimum, the smallest, over lambda max. Okay? So you can see, of course, that the closer they are together, the faster this converges. And when people use the Ntk, for instance, for pruning or for neural architecture search, and I'll get to this hopefully in some other, like either tomorrow or the day after, what they do is they say, oh, this is my metric of how well this trains. So I want this thing to be small, I want this thing to be large, okay, because then I train fast. So let me design my Ntk so it's fast. So I compute all the Ntks for all the network before I prune it, and then I prune one by one and check what it does to my condition number, and I pick the one where the condition number suffers the least, becomes largest. So this is one algorithm, for instance, that people use. Is that clear? So this is actually recurring. People do this all the time. They write some Ntk, and often they don't do infinite width limit. They approximate the Ntk by simply taking, where's my formula? Here. In this thing, they just basically compute this piece. So they just do a Taylor. In fact, what they do is a Taylor expansion of the neural net. They take the first order term, they build the Ntk, they call it the empirical Ntk, they compute a few or they compute one, they look at the spectrum, okay, and then they look at these condition numbers and then they say, oh, we're gonna greedily go in the direction where the condition number is, what has it to be, largest, because that's the direction where we train best. Seriously, there's a whole bunch of algorithms like this which kind of work but aren't so well understood, although the intuition is kind of clear. All right, so this allows me now, if I may, I'm sorry, whoever I'm going to bother, I just want to show you a few pictures because there's a whole line of research. So this one now everybody has probably seen, the one with the random labels versus non-run. And I'm very proud that this is still staying here on board. So I want you to stare at this one here. This is the one I care about. How do I do this? Like this. Okay, this is the expression. Yes?
The condition number is typically max over min, right?
Yeah, so I was afraid if I mix this up and it's 1 over. That's why I looked. Well, you understand what I want. What I want is to converge fast, so whatever it is that it takes. So I guess I want this number here to be large, so I want lambda min over lambda max to be large. And what did I write? Yes, I want this one. So whether it is the condition number or not, but I want this to be large. Okay? I thought this was the condition number. It could be 1 over the condition number. Yes, you're right. This is 1 over the condition number. Yes. Okay. All right. So now, having said all this, I hope it becomes, those who know this are now bored to death, but those who don't, now it becomes exciting because what this paper did is they computed some Ntk. I think this is just 2 layers something, relatively easy to compute. And then they simply projected, right? They looked at the eigenspectrum and they checked where does my MNIST data project on the spectrum of the Ntk. And lo and behold, for MNIST, it's all concentrated on the top eigenvalues. And indeed, lo and behold, the thing converges relatively fast when you train on MNIST with correct labels. And then when you screw up all the labels, then you get the whole spectrum and it trains very, very slowly. Okay? So there's another thing here. Let's assume MNIST would have would have ended here, literally. I mean, let's cut it off, let's whatever. Let's project MNIST on these 5 or whatever, okay? And let's ignore the rest. And it's kind of nearly like MNIST, assume, right? So then effectively, my NTK is much, much smaller. I mean, there's all this other space, but it doesn't really exist for the data, right? It's effectively low rank for that data, okay? And then there's other, here in these convergence results, let me see. There's other results that Yasserman also wrote down. Yasserman wrote, she said, if lambda min is bigger than 0, which in my language means it's constant, it doesn't go to 0, it's constant. If it's constant, then all the measures that she wrote down, they scale with 1 over n or 1 over square root n, right? But the real statement here is that they scale with poly, basically 1 over n, and lambda min. All these statements about how the NTK becomes an NTK, whether it's constant or not, okay? So in other words, they scale actually with this lambda min. So if effectively we make here, okay, maybe lambda min is very, very small and we scale badly, right? But if effectively we scale much better because the data sits in a high subspace, what does it mean? That means that we need much narrower networks to get the same convergence results. Okay, so and that's also been observed that with a narrow network, you can learn data that isn't so spread out over say, Fourier spectrum or something. And then for other, you need wider networks. Again, so these trade-offs, which all come from this beautiful theoretical work, you just operationalize them in order to make these statements or to explain some of these statements. Does that make sense? All right, so I have this picture. The same for CFAR, and as I already said, it's a more complex data set, so it's more spread out. But when you randomize the labels, you're totally lost. It takes forever to learn, as you can see here. And I don't want to go into this because it's beautiful work. There's a ton of papers in this, but I want to give you the flavor of these papers. And so what has been observed, and there's also nice empirical work actually by a student of Boas, with Boas, that shows, okay, take a neural net and you want to learn some data. And there's this kind of sort of spectral bias. And what it says is, folklore, it says a neural net learns functions of increasing complexity as it learns. So first the simple stuff, and there's some works, quite a lot actually, that say in the beginning the neural net kind of learns the linear stuff, or is kind of linear. And you can make this formal in various models, and there's beautiful work on this. And then it becomes more complex and learns more complex stuff. Okay, and so one way people have tried to make this precise is to look at the Fourier spectrum of the data. So construct data, for instance, here, the data is made out of 2 sine waves with frequencies 1 low and 1 high, 4 and 14. And then they study what the neural net learns. And slowly it learns the low frequency spectrum piece. And only when you train it and train it and train it does it learn the high frequency piece. So this is just one instantiation of this spectral bias. And what people do is they basically use, one line of work uses this kind of view with the NTK. And let me just flash all these works at you. I mean, I can share these slides. I mean, there are many more, but this is just already the ones. And then they compute spectra you can compute these spectra. I mean, you can write down these NTKs. Yasserman has done it. And, you look in these papers, or you look at the libraries, you can do it numerically. You can write down the NTKs. You can look at their spectra. You can model the data, for instance, on the sphere and and then model functions on the data with high or low, Fourier spectrum. And you can see what is learned first and what is learned last. So you can, with the NTK, you can actually compute that stuff and make statements, right? And also see why narrow networks learn low frequencies with that argument that I made, wider ones in order to learn more complex functions. Lots of work, very beautiful one. If you love Fourier analysis, there's much more to do there. I'm not going to go over it. I just wanted to give you the flavor of this type of, I call this practical application. I'm not sure how practical it is, but at least something that the NTK gives us a whole new view on. Okay? Questions? Yes?
I wanted to ask what roughly controls this minimal eigenvalue of the K?
What roughly controls it? Okay, so yeah, that's a good question. Well, empirically, as I said, so MNIST seems to lie on the. It seems, so when they write certain NTKs and they do Fourier analysis, it indeed seems to coincide with kind of low frequency spectrum, low degree polynomials in other views and so on. I don't have a full answer to this, but in these models, they seem to see kind of the low complexity piece, the close to linear piece first, and then the rest. Yes?
So maybe I can make a comment about that.
Please.
So one way you think about it for any kernel method in principle is if you just write down the features underlying the kernel method, each data point is embedded into a high-dimensional, possibly infinite-dimensional space by one of these feature vectors. And then it's a question of how linearly independent are the resulting vectors that you get. The smallest eigenvalue is something about just how much of an n-dimensional space do you span when you take n examples that do it this way. So it's like if they're well separated, you can easily classify them with a linear method. You'll have a small, or a large smallest eigenvalue. Maybe that's one way of saying.
Okay, so let me pass on and be even more pragmatic. So this was also mildly pragmatic. And now I want to even be more practical, as I said. So what do people do? As I told you, they literally just look at the theory here and then they say, okay, let me apply it. It might be half wrong, but I might get an algorithm out of it. Why does it work? Because the algorithms we currently have are so terrible for many things that even, kind of a half hammer can improve things. So that's my take of it. So what do people do, right? They start with some problem they can't solve for neural nets, and I'll show you just one in a second. Data distillation is a good one because you can see why it doesn't work, why it's ugly. Then they write an Ntk. They solve it because you can. They take a deep breath, and it kind of works. So let me show you one instance. I will show you this, and I'll build it up by first showing how horrible it is. But let me speak about data distillation. And then once you go to a kernel, you can always, and Nikos always asks me that question, why the Ntk and not any other kernel? And I don't have a good answer except it works. But maybe one of the answers is that it does actually correspond to some neural net in some limit, right? It is somewhat architecture specific. It's not just some Gaussian kernel. It literally has the architecture baked in sometimes. It kind of has the compositional elements that neural nets have, and I don't know what else to say, but basically because it works is the answer. But there is some justification. Why an Ntk and not another kernel? Right, so let's speak about dataset distillation. I'll give you the background. And then as it turns out, at least until, I think it's still true, but progress is being made. This is actually the Ntk version. The Ntk algorithm for this problem gives actually state-of-the-art results. It's the best for now. So what is this dataset distillation? So what does dataset distillation do? So there are all kinds of distillations. You might have heard of knowledge distillation. Who has heard of knowledge distillation? Okay, either everybody's asleep or I doubt that. Probably everybody has. What is knowledge distillation? You take a big neural net, you make it a small neural net. How do you do it? You take the big neural net, you train it. It does this thing. It's at inference stage. And then you train a little one, not just on the output, but on the whole soft probability distribution on the outputs. Right? You must have seen this. And when you do this, you can distill the big one into a smaller one. So that's work by Hinton, and also I think it was observed earlier, but that dates to prehistoric times, like 2015 or something. So dataset distillation is a bit newer. So that was first proposed in 2018. So it's still kind of old times for neural net research, but a little more modern. So what is the idea? The idea is that we have this huge data set. We train a neural net. It's kind of a lot. Can we reduce the data? Can we train it on less data? And of course, let's not ignore, there's tons of literature on which data samples to pick out of a data set to kind of let the thing learn. And if you think, for instance, right, is the problem clear? So we don't want to use all this data to learn. We just want to use a subset or distill. I'll say what distill means in a second, but reduce the data to get the same model, to have the model learn the same thing. Yes?
So is it the same as active learning, offline active learning?
Is that the same? No, it's not in the way I present it, because I'm really going to mess with the data. I think active learning is more like curriculum learning, how you... No.
Picking examples of the data set.
Oh, it's picking the ones that are best for you. Yeah, so this would be active learning. Here, I really want to distill a whole data set using a model. You'll see the difference in a second. But of course, these are related topics by reducing the data. But the point is, let's think of SVM with, yes, Nikos.
One comment.
Please.
In data distillation, the data change. You're not only picking data.
Yeah, you will see. I mean, we're messing with the data. You'll see it. They're beautiful pictures. That's why I have slides, actually. Otherwise, I would have done everything on the board. So think for a second about SVM, support vector machines. Let's assume the data is linearly separable for a second, right? And you have lots of data points, and you learn. But what do you really need to learn? Which ones matter? Usually only the ones, yes, sorry, you want to give me the answer? No. Usually, like when you have a support vector machine, it's enough to have the ones on the margin. That's enough to learn your separator, right? So you can see already a way that you can compress the data, but that's more in the Lenka spirit of picking the ones that you want to learn. Actually, no, the support vectors, are they? Yeah, so never mind. But I don't want to go too much into it. But you can see that data can be reduced, at least with respect to a linear model. Now, the other question is, why would we care about a small data set? I mean, I personally find it already attractive to think that there is a small data set that allows us to learn the same thing as a big data set. I mean, that's attractive to me as a thought. But we also understand something about generalization, because as you will see, the synthetic data set that we extract looks different from the real one, from the initial one. I'll show you pictures. It's a bit like dimension reduction, maybe, or I don't know. But in any case, algorithmically, for those who care about algorithms, there are lots of algorithms nowadays for pruning, as I told you, and neural architecture search, where people continue learning, also not to forget, where people, in order to find the right network, for instance, to prune it, they need to retrain on the data set again and again and again. So I take a big network, I train it, I check which connections I can cut, I cut them, I train again, I cut, I train, right? So it's very intensive because you need to constantly train on the same data, on the big data. So if we had a smaller data set that reflects the model, you can speed up these algorithms for pruning, for architecture search. In continual learning, what do people do? So you train a neural net on one task, you shift slightly and starts forgetting the first task, right? You know that. What do people do? I mean, there are various ways to mend the problem, but one of them is to keep a few examples from the old data set. Like when you learn a language and you never speak the old language, you'll forget it. But if from time to time, like somebody for 10 minutes calls you and speak in that language, every day you will not forget it. I see it with my kids. So that's like the continual learning. Amending is to replay data. It's called replay. And what better than to replay it with good data, with synthetic data that actually, have the model, keeps the learning up. You following? Is that okay for the motivation? All right. Oh, I want to make one excursion into, so why can we distill data? I think one reason is perhaps, and again I'm speculating here, that we know that common data, I mean we hear this all the time as a wisdom, MNIST, CFAR, it's all low dimensional. Yes, it lives in this 150 image net. One image has 150,000 pixels. It's a lot, right? We know that we're not in the 150,000 dimensional manifold, right? So there is this wisdom that data is low dimensional. So I want to just give you, because I think Sarah mentioned it in her talks, but I'm not sure how many people actually went there and listened to it. So there's this paper that people now cite all the time. Who has seen this? Okay, I see a few hands. Do you know how it works? So anyway, so this is I like this paper, even though they don't do much science, but they do a very thorough analysis of lots of data sets, and they compute their intrinsic dimension. So what do they do? So this is just an excursion, as my students know that I like to make excursions to teach things to people which has nothing to do with anything else. But so here's what they compute, and I'll tell you in a second how they compute it. So MNIST, for instance, with various ways to compute it, and I'll explain how they do it in a second. MNIST, for instance, only has kind of 10 dimensions. That's it. This is the street view thingy, these numbers, these photos of house numbers, a little more. CFAR a little more, ImageNet, okay. I mean, we're getting there to, 46 or something, right? So that's common. You have seen this, right? I mean, everybody has heard that. Okay, so how would you compute such a thing? I think I don't need the NTK anymore. So does anybody know how these things are actually computed? Sorry?
Distance between points.
Sorry?
Distances between points.
Distances between, you're very good. So let me just quickly tell you how it's done because I think it's cute and also might give you an intuition, maybe, when I start talking about robustness. Maybe it gives us some intuition, although I'm not sure. But it's always good to get intuitions about high-dimensional spaces, okay? So the way they do it, is there any, yeah, here. So the way they do it, they say, okay, there's this manifold, and it's sitting in a big manifold, but all I know is I get points from that manifold. That's like MNIST. I get points from that image space. How on earth am I supposed to find out what dimension it has? And so just to give you, let's assume it was all spheres, okay? Just we distort it later, but let's assume all our manifolds were spheres and d-dimensional. So spheres and d-dimensional, or balls, I should say, maybe. Balls in d-dimension, ball. D-dimensional ball, okay, just for now. So, and let's assume this is, whatever, some radius, 1, all right? And so what they do is, let's assume that's our manifold, and all we get is, say, random pixels from the manifold, some Poisson process, whatever. Every pixel, you get each point with equal probability, Poisson distribution, right? So how would you know what the dimension of this manifold is? One of these algorithms, and most of them, rely on distance between nearest neighbors. So what do? Here's my point. So they take a point on that manifold, right? And then they sample randomly in that volume. So most likely, as you know, all the volume of a sphere sits where? If that's a ball, I should say. If it's a d-dimensional ball, half the volume, say, or a good fraction, I mean 90%, whatever you want, sits in what distance from, let's assume the whole, let's make it easy, let's say this is 1, okay? So this is a sphere of radius 1 in d dimensions. Where does most of the volume sit? It sits, of course, on this ring, but how thick is the ring? Yes, okay, so you're too sophisticated. 1 over d, okay? Let's not bring the e number in. So why is that so? Because so I'm saying basically half of the volume, let's say half or 3/4, 90%, okay, 90% or 99% of volume, right, is in a ring, is between radius 1 minus 1 over d, and when I say 1 over d, I mean constant. I don't know, c, let's allow constant. 1 minus 1 over d and 1, so the radius is 1, right? So 1 over d is the distance, right? Because when you take this to the power d, right, which is the volume of the inner ball, the outer ball, then this is roughly a constant, right? It's e, whoever, right? So it's a constant. E and 1, for me, it's all numbers, right? So we know this, and then let's use it for our manifold thing. Let's use it to find out what the dimension of our manifold is. Now we start sampling, and we know most of the stuff is within 1 over d, okay? So what people do is, and this is the k here, they sample k points from the manifold. I mean, first they get x from the manifold, right? Then they sample k points from the manifold with this Poisson process randomly, so that it's proportional to the volume. Most of them will sit within 1 over d, except we don't know what d is. So what do? I mean, we do just some math. So we write this tk of x is the distance, the maximum of the distances, right? Distance. Or let's just say, you know what, we'll make it easier. Let's just order the points. Let's call them x1 up to xk, the points we sample, okay? And let's say that the distance, they are ordered in distance. Let's just say even, whatever, dx2, right? So I just order them the furthest away, it's called xk, right? And that's my 1, so that's the point here. So that sets my scale. I look at all the distances. All I need is distances, that's it. I look at the farthest point that I have, and then I compute these ratios. So let's call these distances, it doesn't matter, let's call them like what they are. So then I compute the ratio d of xk divided by d of x, the other points. I take the log. Let's see if I got it right. I don't want to write something wrong, but I think that's about right. I take the log of this. Yes, I sum them, right? And then I take an average, and I take the inverse. And this is an estimate of the dimension for this point x. Let's call it m maybe, mk. Okay, depends on k. So what have I done? Let's just quickly recap. Most points will be within 1 over d. Okay? So for most points, think of this as being 1, right? This is my scale. This one will be 1 minus 1 over d. So I get 1 over 1 minus 1 over d, which we all know is 1 over d. 1 plus 1 over d. So the whole thing is basically 1 plus 1 over d to first order, right? Right? 1 over 1 minus 1 over d is 1 plus 1 over d, and now I take the log. When I take the log, I get 1 over d. I average all these for all these points, right? And then I take the inverse, so it's roughly d. So think for a sphere, you actually roughly get the right thing. And this is one of these measures that is pretty stable against deformation and all that stuff. I mean, don't want to go into this, but this is how people do it. And this is how these people did it. They just assumed MNIST is kind of randomly sampled. For every image, they kind of looked at the neighbors, so to speak, and they computed these distances. And k is just how many neighbors they considered, because they didn't quite know. I mean, this is not it's not a Poisson process, but it's pretty stable with respect to k once k is large enough, and that's the dimension. You're looking at me as if yes? Yes? Sorry, was there a question?
Yeah.
Okay, okay, let's start upward. Okay, yeah, go ahead. Yeah, go ahead.
I'm familiar with some related methods, but they're by works by Alessandro Laio. But there is this kind of trouble that for the number of samples that we typically have in these datasets and the dimensions, even if I truly generated the data high dimensional, this kind of method will estimate a relatively low dimension because it's simply not enough samples. I have in mind like that for MNIST, even for the sizes of MNIST, it will still estimate 30 even though it's 800 dimensions.
I see. So I mean, these people here do some check, and what they do as a check is they actually get a GAN to produce MNIST in this case. ImageNet or CFAR images, right? So with the GAN, they can control the bottleneck dimension, right? So they have an upper bound and the dimension. They use this GAN to produce really images that are better randomly sampled, and then they check, and it's kind of in accordance. So they pick the method that kind of is in accordance with what's real. But I mean, there's lots of criticism. I agree with you. This is not perfect. I agree. Yes, go ahead. Please, Nachi. I agree. I just wanted to give it one intuition. Yes, but this paper uses this one. Sorry? So they have checked a few other methods, and then they have said why they are not as good for MNIST because they are more dependent on whatever, not being fully uniform, etc. But they did check. I mean, you can look at this paper. They did some checks, yes. There was one more question somewhere up here.
Yeah, I was about to ask if we can also do some effective dimension with entropy estimation, and how this measure would relate to that.
Yes, the answer is I don't know, but I presume there is all kinds of, I don't know. All I wanted to say is we live in a low dimension. This is good for our intuition building, right? For instance, adversarial robustness, it's kind of interesting if you think of your data manifold as a low dimension embedded in a high dimension, it becomes somewhat clearer why some adversary can screw you up towards a decision boundary, because the decision boundaries in these spaces do all kinds of weird things.
That's why I was not suggesting to compare different methods, that I agree, okay, it's complicated, but just to have the same number of samples and dimension, but generate truly Gaussian high-dimension data and apply the same method, just to have a baseline of what will be the...
I think that's they did. So if the data is provably dimension D, whatever it is, I think they do get dimension D, whatever it is. They don't? Okay, well, again. Okay, we'll need to take it. I need to do my research better, but at least there's all this is heuristics. I mean, again, just checking nearest neighbor on a data set MNIST where we don't know how random it is yes.
So do you know by chance if they check that the dimension they estimate is kind of consistent locally? Like, it's possible that MNIST has like one dimension somewhere and another dimension somewhere else.
You mean all the cats have one dimension, all the dog another one?
For a thing, it doesn't sound totally crazy.
Yeah, I think they do quite. This is a nice paper, this is not very original, obviously, and these methods exist since 20 years at least, if not more. They do some nice consistency checks to see that things work. I don't know about the cats versus dog answer, but I think it's pretty uniform, that dimension. Yeah. Yes. All right, good. Can we go on? Because I actually want to get to data set distillation. So having said all this about the dimensions, maybe it's understandable that we can try to compress our data to some lower dimension. By the way, this is also useful to think about perturbations of the images, right? What does it do to the dimension? You can think about, in this picture here, if you live in a high dimension, you do Gaussian perturbation, it actually doesn't matter that much if you think about it, because it mostly is in an orthogonal dimension, and so, you know, the adversarial one could matter. I mean, thinking like this, I'm not saying this is all precise, but it's useful as a picture, even though it has nothing to do with NTK. Let's get back to the NTK. What do I want to say? I think I said my thing, so let's keep on going. So data set distillation does compression of the data, but with respect to some model. And I'll explain what it does in a second. Do I want? Yes, so I need maybe let's see. I hope I can do it on this board. It should be enough. It's not very complicated. What people do, you'll see how ugly the algorithms are, and then you'll appreciate how the NTK is really, really useful. So what do people do? They just do the dumbest thing. First, let's do really it's not so dumb. That's the paper of Wang et al. And it was state of the art for a while. But what's the dumbest thing we can do? Well, we have gradient descent. Let me just try to not make it wrong. So we have gradient descent, right? So what do we want? We have our training data. Let's call it XT, training, target, test, whatever, something. This is our training data, right? And we train our neural net on it. And we compute some loss, right? The loss with respect to this training data or some subset, right? And we have the parameters, and that's the loss we compute when we train our big model on the data. Big, when I mean big, it trains on all the data, right? And now what do we want? We want a small data set, XS, synthetic, or what do we, Nikos, what do we call it? Support data, whatever, something small, so that when we train, so what we want to do is we want to do gradient descent on the small data, right? Such that the big model, such we mimic the big model. Okay, so let me write this down. What does it mean to do gradient descent on the big data? Let's see. I don't want to necessarily screw it up. So what are we looking for? And so because people, this comes from the meta-learning framework. So what is meta-learning? It's like this kind of, you must have read these, seen these papers, learning to learn. So what's learning to learn is when you're not happy to set all your hyperparameters, but you actually want to learn them also. That's kind of learning to learn. So they throw into the mix also a learning rate. So they want to learn a data set and the learning rate for that data set such that learning on the little one gives you the result as if it had been on the big one. Okay? So how do we do that? And it's already clear what the kernel can do. Hopefully, with my formulation, you should already see what the kernel solution for this is. But let's just do it pedestrian first. So what do? So these ones here are, so what do you want to compute? Now, having said all this, you want to compute the argmin on some data set. And this is not just one data point. This is a small, let's think, what people did here, these Wang et al., what they did is they did MNIST with one image per class. So 10 images of MNIST. Okay, one per class. So think of this as 10 images from MNIST, XS. So X, this and this is argmin of this and this. So we're minimizing over all learning rates, over all data sets, such that what? The loss function. So what do we do? So first, we do gradient. We start with an initialization. Our model is always the same. For the big data, for the small data, same model. We initialize our model, right? Then we do gradient descent. And because it's really, really awkward, let's do one step of gradient descent with our learning rate. So we do gradient descent, right? On the loss function, on our synthetic data XS, right? So we do that, starting from theta 0. Right? So this is one gradient step on the synthetic data. And now, what do we want? After having done this, we get these parameters, and now we compute the loss of, on the big data set, the one we care about, with the parameters that we have gotten by doing gradient descent on the small one. It's really, why is this so awkward? Because it's very hard to, because here, argmin means we need to now take a derivative with respect to S and the learning rate, XS and the learning rate, right? So this is the awkward thing. The awkward thing is we need to, of course, ideally, we don't want to just do one gradient step. We want to have the model, we make it learn, we do all the million gradient steps necessary, right? The model is done. Then we evaluate it on the big data set, and we want to get something that is similar. And then we would have to propagate back, when we compute the derivative with respect to xs, we would have to propagate back through all these gradient steps. Horrible. I mean, you can't do it computationally. This is what I mean when I say anything you would want to do with a neural net is just horrendously ugly, because you can't do it. Do you realize is it clear what's difficult about this? It's clear, right? Because, all right, but this is the Wang et al. Algorithm. So what do? Maybe I'll just, let's see if I have it. Did I have it? Yes. Let's just not write it down, but let's look here. So what do? They do something a little more, oh, sorry, no, let me actually not kill the tension of this. So they do this. So what do? Let's see. What they do is they initialize their data set, right? So they initialize some data set. They start with some data set from some distribution. Usually you pick a subset of the data, but you could also start with a Gaussian, whatever you want, right? And then what they do is they pick an initial distribution from some distribution also, right? This initial distribution. And then they do one step of gradient descent, right? They do one step of gradient descent, theta 0 here, on the loss function on this thing with theta 0, right? Just like I wrote. They do one step of gradient descent. They evaluate the loss on the big data set. And for the big data set, they usually take a sample. So then xt is a sample or batch of the big data. Batch of the big data. And they evaluate by computing the loss on this sample with this theta 1, which they have obtained by optimizing on the little one, right? Right? And then they take a gradient, an update, xs. They update it by taking the gradient with some learning rate, alpha, okay, with respect to xs, with respect to this data, right, of this whole thing that they've just evaluated, L, right? And the same they do for the learning rate. All right, and so the learning rate they also pick somewhere at random, whatever, from some distribution, all right, random, okay? So you see what they do? So they pick some learning rate, they pick some data set, they do one gradient step, they write this down, they evaluate the thing, and then they propagate through all this expression to update the data and the learning rate, and they repeat, usually. That's how it's done. You converge on the data, right? You have to stop thinking of, we're now walking on the data, we're not walking on the parameter space. We're also walking on the parameter space, but we're also walking on the data. So we have a gradient with respect to a gradient. A horrible thing. You're following? So this actually works quite well, and you see what it does. So when they do that, they distill images from MNIST like this. They look very horribly noisy, right? Not nice. What's the problem with this? The problem is that when you do this, you're really, really good when you start your big model with the same initialization. But the moment you switch initializations, you're screwed. So the data hasn't learned anything about the data, actually. It has basically learned something about the data, but a lot about the initialization. Okay? That's why it looks so horrendous. Okay? All right. And so, yes?
Can you repeat this? I'm not sure I understood.
Yes. So here, what I did is I picked one initialization. I made a gradient step on the data with that initialization. Then I kind of think of initializing the other model that learns on the big one with that same initialization, right? As if, right? And then I make the data such that the big one learns as well with respect to that original initialization, theta 0. But the moment the big one has another theta 0, everything breaks down. Right? It's very much dependent on where you initialize this whole process. Not nice. Okay? Following? Clear. So far clear. All right. And so the real algorithm.
But couldn't you draw the initialization every time?
Very good. Yes. So yeah, that's exactly what they do. So what they do is they repeat that thing and they keep sampling with different initializations, right? And so they sample these initializations, and then they compute various loss functions. Each time with respect to that initialization, they sum them, and they average over these initializations. So instead of doing it with one starting point, you do it with various starting points, and then you walk kind of so to satisfy them all. Is that kind of clear? Yes, it's ugly, right? I mean, it's a nice algorithm. It's a nice, whatever it was, Europe's paper. But I mean, let's think, I mean, we kernel people know that this is ugly, right? Is it clear what's done? Okay, and just to give you the background, so what I said is you start such that you satisfy the maximum number of initializations. This is actually part of a much larger framework. This is just really one of my excursions. This kind of idea has been used widely, for instance, for few-shot learning. So what is few-shot learning? This is something where you want to learn in a way that when a new task comes along, you only need to see 2 of them. Like when a human sees a tiger, we run, and we do this once. We see one tiger, we run. We don't have to see a million tigers first coming towards, right? So this kind of philosophy is exactly the same algorithm. So what people do is they train on multiple tasks, and then they average the loss function, and they make a step and gradient space. Similar, everything is similar. Maybe that excursion confuses you more than not, but I'm saying this is a framework of meta-learning which appears in various guises all over the place, okay? And mostly it's state-of-the-art, this kind of ugly stuff. Unrolling the computation, propagating through, and so on. This is usually state-of-the-art. All right, so the next one, I'm just going to give you philosophy now. I'm just quickly the progress. So that was 2018. It gave you some progress. They did something. Let me give you maybe the benchmark number. They did pretty well on MNIST, I should say. How well did they do on MNIST? I didn't even write it down. Oh, they didn't do so badly. With 10 images, I think they got to 79%, so nearly 80%, with just 10 images on some standard architecture. Not so bad, right? I mean, for learning on MNIST, but it's MNIST nonetheless. So then there was follow-up work. First of all, the first realization people had is, why on earth are you just learning the data? You might as well learn the label. For MNIST, it's you say it's a one-hot vector, right? It's whatever MNIST, 0, 1, 2, 3, up to 10. It's a 10-dimensional vector. Why do we need to have 1 and 0, 0, 0? We can have soft labels. So you can easily adapt this thing to also learn the labels of the synthetic data, right? That was another NeurIPS paper a year later, or maybe ICML. So not very sophisticated, but got some progress. Not very much, though, but like a couple %, right? So that was one thing. And then there's actually interesting work that says, why do we need to learn the data? Let's just learn the labels. And that also got some progress, right? Another NeurIPS paper. That was easy times with NeurIPS. Nowadays, it's much harder. Anyway, so the next one they did is they said, okay, this is kind of ugly, all this stuff, let's not do it. Let's match immediately the gradients that the model gets with respect to the data. So they define some distance on the gradients. They do that, and they get a bit more progress, okay? And then there's, I think the latest state of the art is not much better. Just to give you a flavor of how bad it is. The latest state of the art, what they do is they say, you know, we can't, ideally we would like to do all these gradient steps, but we can't. And then propagate through them. That would be the ideal thing. Let the thing learn, propagate through the whole learning, optimize the data. But you can't do this. It's too complicated. But let's have many trajectories. Let's run 100 neural nets, right, that learn on big data, so to speak, and then optimize the little data to match these trajectories with the gradients, right? Or with just on that they match learning on these trajectories. So you basically, you cheat a little bit with this algorithm by doing a few steps at various points in the learning process. Again, I'm just being very vague, but this is the state of the art with this, when you do this trajectory matching, so you just say, let's train on real data, then train a bit on synthetic data, compare it what would have happened with the real data, match the gradients, and see what you do, propagate through, get the data. So that's the best state of the art in this. By the same group that did the first data. This is like 21, or Nikos, is it 21 or 20? This is like recent. Oh, 22. There you go. That's the state of the art. Yes?
So do you need to train this large model in the end? Or?
Yes, you first train all these last models. All these big, I call them big, but train them on all the data, write down all the trajectories, save all this in the memory, and then when you want the little data, you do this by matching various trajectories. But then, the good thing is then you end up with 10 images, and then you throw away all that, you did this once, and then you can give it to everybody else in the world and say, now you just need to train on these 10. So it's very computationally intensive, but the output is reusable, and tends to be also somewhat agnostic to architecture sometimes, right? So it's, or models at least. Right. All right, so that's what they, not so bad, right? This is the distilled, so in terms of how I mean, you learn something about the images. I like to stare at them. It's cute, right? I mean, what do they learn? How does the quintessential banana look? Apparently something yellow, so that's good, and then not clear, right? So it's cute to look at them because that's what a neural net basically learns, right? If you had to produce the best image with respect to what this neural net learns, these are the images you should use.
Do you think it's really the most I would guess that it's like supervectors, right? The kind of ones that
Yes.
more confusing ones.
This is with respect to what the model learns. So this is with respect to a learner. So I don't know how to interpret these, but it's also interesting to look at the manifold on which they lie. And the next paper does it. And it turns out to be slightly more dimensional. But, anyway, pretty picture. What can I say? All right, now let's do, let me just give a bit of background. So we have seen what we've done wrong, right? This is horrible. Training the neural net and then trying to propagate back, what better is there than to use the NTK, right? Obviously, or some kernel formulation. So what do? What we do, instead of this, let me remove this here so that you see, instead of this ugly stuff, we do something, and this is beautiful work by the Google group. It's 2 papers, 21, so both last year. And they're called KIP. We call them KIP. What does it stand for? Kernel Inducing Points. So these are the data point that make the kernel look like it looks like. Kernel Inducing Points. So what do? It's very simple. Now that we know. So we know that in the kernel regime, right? I erased it now, but let's write it back. On our supports, let's see. What do I want to do? Let's just do it right away properly. On our test set, right? Now we check what has the model learned on the synthetic set. We wanted to also give roughly the same output with respect to the loss function on the real set. So let me write it down. So here's the real set. Here is the data it learned on, the synthesized set. Excuse me, what am I doing? No, not quite. Here's the output on the real set. Let's allow me to write K for kernel because it confuses me less. It's the kernel of, this is where we trained on our synthetic set, right? Right? YS. Okay, so what have I written now? All this ugly stuff with unrolling, etc., I could have written in this way. So what did I write? Here is the data I want to learn, right? So when I learn the data, this is the output, when I learn with training set XS on labels YS, right? Then this is the output if I would plug in a different data set, right? And what I want to do is I want to mess with this data XS so that the loss, when I apply it to XT on the real data set, is small. So let me write it down. So what we really want to do, let's see where I have it. What we want to minimize is the so-called, let's call it the KIP loss, is YT, right, minus kernel XT XS, kernel XS XS, right, YS, done. Okay? So this is the whole data distillation problem written with our beautiful NTK, or so any kernel for this matter, but let's assume it's the NTK. So what do? I want to optimize this loss with respect to the training data and the training labels. And that's all I need to do. And you have seen, Yasaman has shown, and I think I flashed some expressions for when neural tangent kernels actually have analytical expressions. Right? I mean, you can actually write it down. It's like R cos x inner product with x prime or something, or complicated. But in any case, they exist, and you can actually take derivative with respect to x. So you can differentiate kernels with respect to the data. And there is now libraries that do that. You don't even have to work that hard, right? So then, I might even be in time. Then here is the algorithm. Much, I hope you appreciate how much more pretty it is than what we have seen for all this data distillation. So what do? Here's our target set, the one we want to actually kind of imitate, the big one, okay, ImageNet. here is the thing that we want to produce, right? And then what do? So here, ignore this line sample random kernel, I'll speak about it, but what do? We sample, so they do it batch-wise, but let's assume we could do it even on the whole data set. They sample a piece of the data, they take the data that they want to optimize, right? They take a piece of the target. Just remember, kernels are hard to compute if they're too big, but it doesn't matter. We can do it on batches. Then we compute this loss, this one here, right? And then we backpropagate this expression. It's an expression that depends on XS on the data. We take the gradients, right, and the labels, and we and update with gradient update, just like here, except here we differentiate the Kip loss, so to speak. And we propagate that back, so we do gradient descent with respect to this loss function, but on X. There are no more parameters theta. We do it on the data. Nice, no? I don't know. Am I the only one appreciating this? So, so that's what they did. Is that clear? Right? Because I want to build on this next lecture and speak about adversarial robustness and how this could be possibly used to solve saddle point problems. So new stuff that I actually worked on in Nikos and others. But this is nice, right? You basically optimize using the analytical expressions with respect to the data. Okay, and when they do this, first of all, they get state of the art, as I mentioned. So always look at the boldface in these tables. So that's here, and this is all the other losers, basically. They don't do well. And these are all these, they wrote the first paper where they used a fully connected kernel. I mean, it's not so easy to actually compute these things. And then here they used the kernel on the convolutional net, the convolutional kernel. And then they evaluated on some convolutional model. All right, so let me say this slowly. The model they use is a neural net. Right? They use the data on a neural net and some convolutional kernel with 4 layers, I believe, Nikos, is that correct? With some width, 50, I don't know. Some convolutional kernel, some neural net. But they use the infinitely wide NTK for ConvNet to produce the data, right? Because that gives the analytical expressions, okay? And so then they use some data, never mind, they use a bit of data, there's a bit of trickery here to get this efficiently done, a bit of augmentation. But the point is they get quite, MNIST in any case, but even for things like CFAR, this is pretty amazing for 50 images per class. So this is 500 pictures for CFAR 10. And even for one image, like on 10 images, they get accuracy. This is test accuracy, right, with a neural net. Okay, so that's state of the art. So that's nice, right? Questions? So it's clear what's done, right? The kernel is an infinitely wide NTK of a convolutional net. Works better than fully connected. It's not so easy to compute, so the batch sizes, they have to kind of balance this a bit. But that's what they get. And this is how it looks. Not that it teaches us more. What I like about this is actually the bottle. Look at the bottle. So this is the original image that they used to start with. They start with this image, and then they keep doing it, and they get to one bottle. So the quintessential bottle is only one bottle, not two anyway, never mind. But, but yes, please.
Do you have a feeling on how much that will depend, in fact, on the support set that one chooses at the beginning?
How much does it depend on the initialization? On which one, it doesn't matter so much. But whether it's Gaussian or a piece of CFAR, it works, Nikos, confirm if that's right. It works better if you start with CFAR, right? With some CFAR initialization or something from the real data set. But it does also work. You just have to work harder if you start with Gaussian initialization. You just start with something. It's just you have to work much harder to get to, and not always it works. It's just like here you give the thing a hint, basically, where to go. Yes. Yeah.
From the point of view of time, computational time, is it better? Is it much worse, much better with respect to normal methods? Or?
Well, these normal methods are not exactly, I mentioned them, right? Compute 1,000 trajectories and match on all of them is pretty horrible. I asked Nikos because he had to implement all that stuff. I mean, how horrible is this?
I think in terms of speed, it's better to work with generals.
Yeah, also remember, it's a small kernel. Here it's still small, right? It's like the XX data set. The thing that you need to invert is just 10 by 10 in the best case, maybe 100 by 100 or something. So it's not so bad. It's quite efficient. They had to do some trickery, pre-processing, get it done properly, but it's impressive, I thought. I mean, I don't know. So this is...
You also use sampling. In that case, you're sampling initializations. I suppose over here also you're sampling the new NTK for
So yes, sorry, you were right. I glossed over this. So what they do, because they want to be a bit more architecture agnostic in their data set, they actually rotate. Oh, where's the data? Where's the here? They actually rotate kernels in this. So they a little bit use the convolutional, and then they use a bit another one without pooling, and then sometimes I don't know if they mix the fully connected in or not, but they try to make this a bit. But this is heuristics, right? They try to have this work on a lot of architectures, and so they mix and match a bit with their kernels as well. But this is not I mean, it just works, but God knows why. I mean, gives more diversity to the thing or something. Yes, was that the question? Yeah. All right. So I'm nearly done, and even on time, I would say. This is what they get from MNIST. This is the stuff they start with, and here they also optimize the labels or not. I mean, so this is the initial set that they start with when they optimize. Here, if they don't optimize the labels, the pictures look like this. If they also optimize the labels, they are allowed to mess more with the picture, is my intuition here. But this is how it looks like for MNIST. And I think they also did it for the other, some other data sets. Here they don't, I believe here they don't train labels, but just evolve the pictures. Okay? And there's there are two observations they make. The data set, the interesting thing here is, remember, you take a derivative with respect to a whole data set, say 10 images or 50 or 100. And so it turns out the data set becomes correlated with each other. So the MNIST 0 and the MNIST 1 are not independent anymore. Why would it be? I mean, the gradient does whatever is good for it, right? I mean, so they become, and you can measure this by doing ablation kind of view, subsamples. So let's say you produce 50 images, and then you throw some of them out, and the performance degrades much worse than if you did it with random images that are independent. So that's interesting, right? You get a correlated data set. I don't know what that means. But also the intrinsic dimension of these images, the one I mentioned, increases a little bit with this. So they kind of go on a higher. Again, this is just I don't know. There's no good science about it yet, but they become a bit higher dimensional if they want to have the quintessential banana or bottle or whatever. Right. Let's see. Yes, so I want to extend this now and get to our own work and also tell you about adversarial robustness, but I think I will do this and give you one more sample complexity lower bound, just so that you know I can do things on the board, but I think I'll do this tomorrow. Thank you.